Alright, so in this video I'll talk about the chi-squared tests for homogeneity and independence. So I did the goodness of fit test part 1 video already, so hopefully you saw that that was basically when you're dealing with one variable, one sample, but you're basically trying to see if the categories, what's happening in the categories is what is expected to happen in the categories. Now for these two tests, this would be more so if you are, one, trying to compare two different populations with one categorical variable, or independence would be if you had multiple categorical variables and you're trying to see if they are dependent or independent. So the first one, for homogeneity, you're basically trying to compare two different populations and seeing if there is a difference. So your null and your alternative hypothesis would basically be saying there's no difference, just as we have with all null hypothesis. We've been saying that there's no difference. But you're saying there's no difference in the distribution between the two populations. And then for your alternative, you're saying that there is a difference. So very much like the other chi-squared tests, remember that chi-squared tests are for categorical variables. So that's when you should be using a chi-squared test. Now for independence, you're seeing if two categorical variables are independent of each other. And so you're trying to basically say that there's no association between the categorical variables, meaning that they're independent. Or the alternative would be that there is an association between the two categorical variables. So remember, if there's no association, they're independent. So you can also say the null and alternative this way, as you see down here, that whatever the categorical variable is and the other one is, that they are independent. And then the HA would be saying that they're not independent. So it's the same as saying that there is no association versus there is association. So you do have to check conditions just like you would with every other test. Very similar to before, but if we have multiple populations, like if we're doing homogeneity, you have to make sure you have a stratified sample where we have multiple groups. Or if you're doing for independence, you're just seeing if there's a random sample, one random sample done. And remember, for independence, you're using one sample, but you have multiple variables, categorical variables that you're trying to see if they're independent. You also want to make sure that the sample size is less than or equal to 10% of the population size. And just like before, the expected count should be greater than 5. Alright, so here's the very first example we have. Notice here, or I'll go ahead and read it. So a random sample of parents with school-aged children was taken during 2019. A separate random sample of parents with school-aged children was taken in 2020. Parents were asked what type of school their children attended, and here are the results. If we're interested in comparing the distribution of type of school for the 2 years, which significant test is appropriate? Well, hopefully see you have two different populations, and we're comparing to see if there's difference between the two. So that's homogeneity. We don't have one population, and we're trying to see if multiple categorical variables are independent or dependent. That would be the chi-squared test for independence. So two populations comparing the same variable with multiple categories would be homogeneity. Here we're trying to see, is there no difference? Well, the null hypothesis would be that there's no difference in the distributions of school types from 2019 to 2020. And then HA would then be the opposite in the sense that there is a difference between the distributions. Remember, we're dealing with categorical variables, so state your null and alternative hypothesis in words. Alright, so checking the conditions, we have two independent random samples, so we do know it's a stratified random sample. It's definitely reasonable to believe that there are more than 320 parents, and in fact we should think that there is definitely much more than 10%, that this would be less than or equal to 10% of the population of all parents in 2019 and 2020. So 320 parents, yeah, we can assume that that is less than 10% of the amount of parents. And then the 214, we can assume that that's less than or equal to 10% of all the parents in 2020. to get the expected counts. So there's a calculator step that we can actually get the expected counts very quickly. Instead of using a formula, there is a formula for this, but it doesn't make sense to spend time doing it. So let me go ahead and show you that. So what you want to do is you want to go to the matrix menu. This is going to allow us to basically enter our table. So matrix menu, if you just go, I'm going to do it on my calculator, second, x to the -1 power, which is inverse, x inverse, so second, x inverse. This gets you to your matrix menu. We want to go ahead and edit the first matrix. So we're going to go to edit. I scrolled over to edit. I'm going to hit enter. We first want to tell it what size matrix we're dealing with. Now the matrix in these screenshots are not what we're dealing with, so I'm going to just go up. So notice those already have the counts. So we're dealing with it's row by column, so there's 3 rows and 2 columns. If this had totals on the sides or the bottom, you would not include the totals. So we have 1, 2, 3 categories here and 2 rows here. 2 columns here. So that's a 3. Oops, I'm actually typing in the wrong place. Let me put it over here. So that is a 3 by 2. So that's giving us the right setup. You'll know if it's right based off of how it looks. And now you just enter the numbers. So I'm putting 266, 163. So you just enter the numbers as they are. 8 and 30. Alright, so now we have our data here. So now we've entered the matrix. So now the next step, if we're going to go ahead and run our test, is now that we have our matrix in there, we're going to go to tests and we're going to go to chi-squared test. So we're going to go to, just like we had before, stat, tests. It stored that matrix, so we're not too worried. I like to go up once again because it's quicker. And then we're going to C, which is chi-squared test. And our observed, what actually occurred in our sample is in matrix A. It's going to put the expected in matrix B. So that's why that's there. And then once we calculate, you will see that it gives us our chi-squared test statistic, it gives us our p-value, and it gives us our degrees of freedom. We did not have to put it in there ourselves. Degrees of freedom is different for the chi-squared tests. Here, your degrees of freedom is calculated a little bit differently, so I'd rather you guys just get it out of the calculator instead of having to worry about calculating the degrees of freedom. So once again, this data here that's in the screenshot is for a different problem, but I just wanted to have the steps there with screenshot. So notice we have our test statistic, we have our p-value, and we have our degrees of freedom. So if we wanted to see what the actual expected values are, you can go back to your matrix menu. So we can go to second matrix, we can go to matrix B, hit enter, and it'll show us basically exactly how it's lined up in our problem, in our table. Go back to it here. You can see and compare it to the blue numbers here, those are the expected values, what we would expect in public, private, home in those years based off of the sample size. So remember that the chi-squared test is comparing it to see, well, based off those two populations, are they different in the expected and the observed values? So we have our chi-squared test statistic, we have our p-value, and remember to interpret your p-value, this is just a reminder here, is that your p-value is basically if your null hypothesis was true, that there's no difference in the distributions from 2019 to 2020, it's the probability of getting a sample like we did. So if you needed to interpret the p-value, you could look over that. But let's go ahead and make the decision. So same as before, we look at our p-value. There was no alpha level given, so we're going to use alpha 0.05. Our p-value is greater than alpha, so remember we failed to reject HO. So we can't necessarily reject this and say that it's not true. So now we just state our conclusion. There is not convincing statistical evidence that there is a difference in the distribution of school types for school-age children. So remember, if you fail to reject this, you don't have enough evidence to say HA. Alright, and that is how you do it for homogeneity. And now let's go ahead and look at an example here where we're having to do it for independence. Same process. So now we have a random sample of 2,000 adults. notice that's one sample. That is how you know if you're doing homogeneity or independence. We have one sample, and they broke it down to different categories, but we have two different variables. We have whether or not they're employed, and then their education. So basically what we're interested here is deciding if education level and employment status are associated. So that's what you're doing when you're doing independence. It's the same process in the calculator, but just stating your hypothesis, your null and alternative hypotheses would be different. So HO, you're saying that there's no association between education level and employment status, and HA is saying that there is an association. Now, if you don't want to say association, you want to use the independent word, then HO would be saying that they are independent. And then HA, because if they have no association, then they're independent. And then HA would say that they're not independent. So you could do HO and HA either way here. Now, when you go ahead and get your expected values, remember you can go ahead and put the matrix in the calculator of the original table. And I'm going to pause and do that now. As a reminder, you go to second matrix. Now we want to edit the first matrix. And we are now making it, remember, it's row by column. So we have 2 rows, 3 columns. So that's now going to be a 2 by 3. And now we can edit it and put in our numbers. Remember, if it includes a total column or row, do not include a total column or row. I'm just entering the numbers. And I'm going to pause to save time. So I went ahead and punched in my numbers in my matrix. And now I'm going to run the test. So stat over to tests. I'm going to go up to my chi-squared test. And I'm going to hit enter. Observed is in A. Expected I want in B. And I'm going to calculate. Remember, you can draw if you like, but I like to hit calculate because it shows my degrees of freedom. So it gives me my chi-squared, it gives me my p-value. Remember, this is scientific notation here, so I know it's really moving that decimal place over 4 times towards the negatives, which is a very small p-value. And yeah, so I can see everything there. I can go back to my matrix, second matrix. I can go to my matrix B to see it if I need my expected counts. So this is what we would expect to occur. And now we can go ahead and kind of proceed here. Remember to check your conditions. If this is a free response question, note that you're checking them. Show that, okay, I'm checking my conditions. We do have randomly selected sample. It's definitely, usually the second one is kind of like we have reason to believe because we don't really always know population numbers, but we can definitely say there's reason to believe that 2,000 adults is less than or equal to 10% of all adults in the population. In 2000. Or actually, I don't know what year this was, but not the year 2000, but the 2,000 adults. And then you're saying, that's why we needed those counts, that all expected counts are greater than 5. So that's kind of why you need to see the expected counts. Otherwise, you can just run the test. So we have our test statistic, we have our degrees of freedom, we have our p-value, if you move that decimal over and around a little bit. And remember, if you need to interpret your p-value, this is how you would say it, basically, is an example of how you'd say it. Remember, it's saying that if our sample turned out that way, and if the null hypothesis is true, then it's this percent chance that that sample would happen, if this is true. So that's kind of what it's saying in a nutshell. And remember, we conclude the same way. So if our p-value is so small, basically it's less than alpha 0.01, even smaller, stronger, we're rejecting the HO. And so for rejecting HO, there is enough evidence for HA. So there is convincing statistical evidence that there is an association, between education level and employment status for all adults. So that is how you do a chi-square test for independence and homogeneity. So these are the things you just want to make sure you do if you are asked for a free response question. Just a reminder, this is basically the process for any hypothesis test. And then I just threw this on here. All these slides, FYI, are adapted from the videos in AP Classroom for the units. I just snipped them to make it shorter. But this is just a quick reminder sheet if you're trying to decide what chi-square test to do. And that is it.